In this lesson, we're going to be looking at a method of getting prime factors called prime decomposition. Since we're looking at prime factors, we'll need to remember what a factor is, and they are any values that multiply to get the number. So if I'm looking for factors of 10, I go, what multiplies to get 10? Well, 1 times 10, remember 1 times the number itself will always work. And what else gets me 10? I can look at my times tables, I can go down the list. I've done 1, I usually then try, does 2 go into 10, and then does 3 go into it, does 4 go into it, and I'd find the only thing that goes into it is 2 and 5. 2 times 5 is 10. There's no other ways to multiply to get 10, so I found all the factors of 10 there. Now we're also going to need to know what prime numbers are, and so remember they have only 2 factors, 1 and itself. And if anything except 1 and itself goes in the number, that means it's not going to be prime. And so 7 is a prime because there's only 1 times 7. That's the only way to get 7 with whole numbers. Whereas 10, you've got another option. You've got 2 times 5. That means it's not prime because you've got 1 and 10 and 2 times 5. So if it's only got 1 and itself, then it's prime. Now we should note 1 is not considered a prime number because it's only got 1 factor, and prime numbers are meant to have 2. Now there's been some question over the course of history whether 1 should be called a prime number or not. We're going to side with the consensus, and we're going to say it's not. Pretty much everyone nowadays agrees that it's not, and so that's what we're going to go with. And also we're going to be expressing numbers in index form, and remember that means if you had 3 times 3 and then times 5 times 5 times 5, you can put that into index form by using those little numbers up the top called index numbers. So this says there were 2 3s that we multiplied, and this says there were 4 5s that we multiplied. So the first thing we want to understand is that factors of a number that are prime numbers are called prime factors. And so if I wrote down all the factors of 12, which ones of those are prime numbers? Well, 1's not, 12's not because 3 times 4 gets 12, 2 is, so we can put a little box around it, 3 is, 6 is not because of 2 times 3, and 4 is not because of 2 times 2. So the prime factors of 12 are just 2 and 3. Now, if I want to express 12 as being multiplied, I could do it with 6 times 2 if I want to. I could also do it as 3 times 2 times 2. Now, notice that 3 times 2 is 6 and times 2 is 12. So it's exactly the same as up here, but notice this time I've only used those prime factors. And the idea is every number can be made by multiplying only its prime factors together. Now sometimes you might have to multiply them more than once, like I did here. I had to do the 2 twice, but that's the idea we'll be looking at here. And notice here I've just done one step further where I've put in index form. So those 2 2's there, I've made it 2 to the power of form. This, what we got here, we refer to as prime factor form, and it's where only prime numbers are used and they're put into index form. And so that is another key point that we're going to be using, and we'll see a bit more of that in the examples. We're going to look at a method now that helps us put those numbers into prime factor form, and it's called a factor tree. Here's how it works. We start with the number 18 because that's the one I'm going to try and put in prime factor form here. And what I do is I draw 2 lines coming off it, and I have to do this times that has to get 18. Now I'm going to pick 9 and 2. And see how 2 is a prime number? I just underline it, and I don't do anything else with the 2. That's it. But since 9's not a prime number, I now do something else. I go, okay, well, let's split this one now. What are 2 things that multiply to get 9? And the key here is you can't ever use 1. And so it's got to be something other than 1 in the number itself. And so the only options here is 3 times 3. They are both prime numbers. Now, we underline prime numbers because we can't go any further than that. If we're not allowed to use 1, there's nothing that multiplies to get 2 except 1 and 2. That's why I underlined it, because I can't keep going. But for the non-prime numbers, we can keep splitting them up until I get like this. See how there is only prime numbers left at the bottom. That tells me what I would have to multiply together to get 18. I would have to go 2 times 3 times 3, because there's a 2 there and there's two 3's. It doesn't matter what order I multiply them in, and then I can put it into that prime factor form where I put the index numbers to deal with the fact there's two 3's here, so it would look like this. Remember, this is now in prime factor form, and that is called a factor tree. Now, I used 9 and 2 here, but what about 3 and 6? Don't they get 18 as well? Wouldn't that give me a different answer if I use 3 and 6? Well, I'm going to try it out. Here's 18. I'm going to split it into 3 and 6 this time. Now, 3 is a prime number, so let's underline it. Here's 6. It's not a prime number. It needs to be split up even further. So put the lines underneath. What multiplies to get 6? And you can't use 1 and 6. The only option is 2 and 3. And I put my underlines there because they're both prime numbers as well. Notice once again I've got a single 2 and two 3's, exactly the same as over here, a single 2 and two 3's. And so once again I get exactly the same answer. 18 is equal to 2 times 3 to the power of 2. Now, so far I haven't even mentioned the words prime decomposition. That's what we're doing here. We're decomposing 18. Decomposing means breaking up into smaller parts. Well, that's what we're doing. We're breaking it up into a single 2 and two 3's. And so this process is actually called prime decomposition, and it's done using the factor trees. Now, when there's zeros at the end of a number, like this one here, that's 90,000, there's a technique we can use to split the zeros off and deal with them separately. And so what I do when I split it up is I put the 9 on one side here, and I put a 1 with all the zeros on this side. So that's 9 times 10,000, which equals 90,000. And then I can deal with the 9 normally. That'd just become 3 times 3. To deal with this, I keep splitting it up. So I'm going to take 2 of the zeros on one side and another 2 of the zeros on the other side. And so that's 100 and 100. So when I multiply 100 times 100, I get this. Notice I'm really just dealing with zeros. There were 4 zeros altogether. So I've got 2 of them there and 2 of them there. Now, when I split up 100, what do? I'm not going to go 2 times 50. That just makes it a bit more complicated. I'm going to go 10 times 10. I'm going to split the zeros once again. I'm going to make it 10 times 10. And I could split these zeros as well. And when I go down here with 10, finally, this is the only time we're not just going to split zeros off. We're going to say, well, that's 2 times 5. That's the only way to get 10, apart from 1 and 10, which we're not allowed to use. And so that would be 5 times 2. Now, I haven't finished this factor tree because I didn't keep going with the 9 and I didn't keep going there. We'll see an example that's like this. But just remember, to deal with the zeros, we just split them off, and this side will deal with all the zeros. This side will deal with the non-zero part. So, a couple of examples. We're going to express 48 in prime factor form. So, write the 48 up the top. Then, write the split things. And we've got to come up with a way to get 48. Now, there's several. We could do 12 times 4. We could do 6 times 8. We could even do 2 times 24 if we want, or a lesser known one, 4 times 16. Doesn't matter which one I use. They'll all end up with the same answer at the end. I'm going to pick 6 times 8. Why? Because they're nice and in the middle, and it's nice and on my times tables. It comes to mind very quickly. So I'm using 6 times 8. Now, let's take this 6 here. I'm going to split that into 2 and 3. They're both prime numbers. I'm going to underline it. Now, what about the 8? Well, the only way I can think of to get 8 is 4 times 2. So I'll split it into 4 times 2. The 2 is a prime number. Underline it. The 4 is not a prime number. How do I get 4? I have to split that into 2 times 2. They're both prime numbers. Underline them both. So what have I got in total here? Just all the underlined numbers, forget all the rest. So I've got 1, 2, 3, 4 2's and a 3. So the way I express it in prime factor form is I write 48 equals 2 to the power of 4 times 3. And so don't forget the 48 equals. Don't forget to say what number you're expressing in prime factor form. Alright, in the second example, we're going to look at one of these ones with zeros on the end of it. We're going to do the full tree. So we write out 1,800. On one side, I put 18. On the other side, I put the zeros. And of course, I have to put a 1 in front of it. So I'm timesing 18 by 100 to get 1,800. And so now, let's do the 18 first. What can I split it into? Once again, I've got two options, 9 and 2. works, or 3 and 6 works. Now remember, you'll get the same answer, doesn't matter which way you go, just whatever you feel best with. So I'm going with 6 and 3, and so the 3 is a prime number, I'm going to underline it. The 6 is not a prime, I'm going to keep going on this side until it's finished, and so 6 splits into 3 and 2, they're both prime numbers, I'm done. That's that side has ended with all underlined numbers. Now this side, that 100, I'm going to split the zeros up into 10 and 10. And so now I'm going to do each 10. This 10 here is 5 times 2, and they're both prime. This 10 here is exactly the same, isn't it? 5 times 2, and they're both prime. And so now all the underlined numbers, remember, forget the non-underlined numbers, they're out, just the underlined ones. I can see 1, 2 3s, and there's 1, 2, 3 2s, and there's 1, 2 5s. And so altogether, that would be expressed as 2 to the power of 3 times 3 to the power of 2 times 5 to the power of 2. Remember, these index numbers indicating how many of those numbers were there. And don't forget the 1800 equals part. We've got to say what number we're expressing in prime factor form. Now, there's just one practice question for this one, so remember to pause the video. And there we go. There's the tree is the working, so we've got to show that. And then the answer here. Now your tree might look a little bit different. You might have put the 10 on that side and the 27 on that side, or something different to that. But the numbers should end up exactly the same at the end. Same answer. So when I did this one, I started by writing down 270, and I split the 0 off to this side, so that was 10 on there, and the 27 I put on that side. And then I worked on the 27. What gets me 27? It's 9 times 3, so that's why I wrote down 9 and 3. 3 is prime, so I underlined it. I still had the 9 there though. That was not a prime number, so I split that as well into 3 and 3, because that's the only way to get 9, and they're both prime, so I underlined both of them. And then I just had the 10 left to deal with, and 10 always splits into 5 and 2. It's the only way to do it. They're both prime numbers, so I underlined them, then I just counted them all up. There's a single 2, there's a single 5, and there's 3 3s. Now it doesn't matter what order you put these in here, it doesn't have to go lowest to highest, so you could write 2 times 5 times 3 to the power of 3, or whichever way around you wanted to, as long as the only one to the power of 3 was 3. So here's another practice question if you need to have another go. Remember to pause the video. And there's our solution for that one. And that's the end of this lesson.